So in this lecture, we're going to apply our knowledge of uniformly accelerated motion to look at two examples. The first example involves two cars. You got two cars, A and B. They're moving in the same direction with a bumper-to-bumper separation of 4 meters initially. And they're moving at the same speed with car A ahead of car B. Their speed are both equal to 25 meters per second going forward. Now at that moment, which we call t equal to 0, the driver of car A sees a dog. Okay, so you have this dog here. You have this dog here in front of driver of car A. So that's the dog here. So car A, the driver of car A sees the dog and slows down. Okay, he slows down, trying to avoid the dog. And the acceleration is negative 6.0 meters per second squared, negative because he's slowing down. I'm assuming the forward direction to be positive. So this is the positive x direction. So the acceleration is negative because he's slowing down. Now, in the meantime, car B, which trails car A, doesn't slow down immediately because it takes half a second, 0.50 second, for the driver of car B to realize that car A is slowing down. So he then applies his own brake and slows down at a greater rate of negative 8.2 meters per second squared. All right, so there is a time delay due to reaction time of driver car B of 0.5 seconds. So question is, what's going to happen next? Will there be a collision? Will car B hit car A? Because after all, there is a time delay until he applies the brake, right? So that's what I want to find out. And there are steps you can follow, A, B, C, and D. So in part D, finally, you'll reach the conclusion whether a collision will take place or not. Now, think about it. Initially, they're moving at the same speed, right? And they both decelerate. And we know B decelerates at a greater rate than A. So if they start to decelerate at the same moment, of course, car B will never hit car A because it's going to move slower than car A. The only problem is car B takes half a second to realize that car A is slowing down. So by that time, he would have already traveled a certain amount of extra distance with the same speed of 25 meters per second. And then he begins to slow down. At that point, car A has already slowed down. Now, after a while, assuming no collision has taken place yet, at some point, due to the greater rate of deceleration, car B will eventually reach the same speed of car A, even though he started to decelerate later, right? Because he decelerates at a greater rate. Let's say that time, the moment when they have the same speed is T1. Suppose by that time, the collision has not taken place yet. Will the collision ever take place? Well, think about it. After the time T1, they both continue to slow down, but remember, they already have the same speed and B slows down at a greater rate than A, right? So after that, B will be slower than A, which means the gap between them will start to increase and a collision will never take place anymore. So the strategy is this. Let's first find the time T1, the time it takes for car A and car B to reach the same speed, assuming for the moment that there's no collision yet, okay? And let's look at that, what happened by the time T1. Car B has moved a certain distance forward. Car A has also moved a certain distance forward. Let's see whether a collision has already taken place or not by that time. How do you know a collision has ever taken place by that time or not? We'll look at how far B traveled versus how far A traveled. Now remember, B can travel a little bit further than A because after all, he started out a distance of 4 meters back from car A. So B can travel up to an extra 4 meters than A by the time T1, and still there will be no collision, right? So he gained on car A with a distance of no more than 4 meters, and he's still behind car A. And if by that time he didn't travel further than car A by 4 meters, which means he's still behind car A, then they're safe because after that, the gap between them can only grow, not decrease. Okay, so let's find T1 first, and then let's find how far B has traveled by that time T1 and how far A has traveled by that T1. And let's compare the distance they traveled to see whether car B has traveled more than 4 meters extra than A by that time or not. Right? So that's the strategy. So let's do that. Okay, the first part of the problem, they ask for you to plot V versus T curve for both car A and car B on the same diagram. That actually will be helpful for you to finish the rest of the problem. So I have here V versus T through the axis. So let's draw the curves of both A and B. Okay, let's draw car A first. Car A starts decelerating immediately at time t equal to 0. So it's just going to be, it starts with an initial speed of V0 equal to 25 meters per second. And after that, we immediately go into deceleration mode. So it's going to look like this. It's a straight line with a negative slope, like this. Okay, and that slope has a magnitude of A1. Right. A1 is negative 6 point something meters per second. So that is, hold on. A1. Okay. In the meantime, car B does not decelerate immediately because, again, remember there's a reaction time, right? There's a reaction time. So let me draw the curve for car B. It starts out still traveling at 25 meters per second for up to half a second. So it's like this. Okay. And then after half a second, he realized that car A is slowing down in front of him. So he decides to apply some brake and slow down at a greater rate. So now that's what's going to happen next. He slows down at a greater rate. Okay, so this is how car B behaves. I'm gonna label something here for you. So this is A2. Okay, A2 is the rate at which car B decelerates once he starts to decelerate. Okay, so this is A2 here, which is steeper than A1, as you can see. And I'm going to also mark the two important moments. Here is the first moment of importance, and that is when car B decides to decelerate. This, as you know, is delta t, which is half a second, 0.05 second. Okay, 0.50 second, that is, right? And another important moment is when the two V versus T lines cross each other. That's right here. That's when they have the same speed. Okay, and we call this time T1. Okay, so as we learned from our discussion in terms of strategy, we're going to find T1 first, the time it takes for them to reach the same speed, and then we can see how far they get both each traveled by the time T1. Okay, so that's the first part. You want to draw V versus T for both car A and car B. So let me label that. This is for car B, and this is for car A. Okay, so that's part A. Now let's look at part B. What is it we're looking for in part B? From the diagram around, at what time T1 would both cars reach the same speed? Well, let's write down how the speed changes for car A and car B. Okay, for car A, it's very simple. VA as a function of time. VA as a function of time. It's uniform accelerated motion with a negative acceleration. The generic formula is V0 plus AT. A is A1 in this case. So it's V0 plus A1 times T. Okay. And then for car B, you start out with initial speed of V0, just like car A. And then when you reach time delta T, that is when you start to apply the brake. So the time that car B has available to him to decelerate is between this moment and that moment. So the time interval for the deceleration is T1 minus delta T. This is the time duration for him to decelerate. So I must add his acceleration times the time it takes for him to decelerate, which is T1 minus delta T. Okay, not T1, but T1 minus delta T. Right? Now, this is also T1. Right? This is the speed of car A at T1, and here's the speed of car B at T1. And remember, they're equal. I'm looking for the moment T1 where VA equals VB. So set VA equal to VB. And then I can find T1. Okay? You can either do the algebra, you just set this, these two expressions equal, and I'm going to spare you some time. I'm going to just write down the expression now. It's A2 delta T divided by A2 minus A1. Okay, and delta T is 0.50 seconds. A2 equals to, what is A2 equal to? A2 equals to negative 8.2 meters per second squared. A1 equals negative 6.0 meters per second squared. So you do the algebra here, plug in the numbers here, you're going to get your answer, and the answer is 1.86 seconds, or to the first two sig figures, 1.9 seconds. Okay. Now, they give you only two sig figures for the A's and for the delta T's. So it's okay for you to only keep the first two sig figures, 1.9 seconds, as your answer for T1. But when you plug in T1 into a formula for other quantities, it's a good idea to keep one more sig figures too, to lower the possibility of round-off error. So you want to keep 1.86 in your subsequent calculation, which involves T1. Okay, so that is part B. So we now found the moment when they have the same speed. So what's next is to find how far they have each traveled by that moment of T1. Okay, so part C is, let's see here. How far would both cars have traveled forward by the time T1 if no collision has occurred between them? So ignore collision for now. Let's see how far car A has traveled and car B has traveled. Again, for car A, just a uniformly accelerated motion starting with initial speed of V0 with an acceleration of A1. So I find the distance traveled by car A is delta XA, or the displacement car A is delta XA. Okay, I'm not going to use XA. I'm just going to use delta XA because that's how far A1 has traveled forward. If you plug in XA, then you must set an origin, right? I don't care what the origin is. I just want to know how far they have traveled from their original location within a time T1. So it's the displacement, not the position that I'm talking about here. Okay, so that is V naught T1 plus 1/2 A T1 squared, right? Uniformly accelerated motion. The time for deceleration is T1. Initial speed is V0, and the acceleration is A1. Now, V0 is 25 meters per second. T1 you already know is 1.86 seconds. A1 is negative 6.2, actually negative 6.0 meters per second squared. Plugging all these numbers in, and you can arrive at a number, and then that number is 36 meters to the first two sig figures, 36 meters. So car A has moved forward by 36 meters. In the meantime, what happens to car B? Car B traveled a distance of delta XB. Now be careful here. The motion of car B is made of two segments. The first segment is between here and there for the time duration of delta T, and that's when the speed doesn't change. It is just V0, or 25 meters per second. And the second stage is when you go from delta T to T1. That is the duration when you actually decelerating at a rate of A2. So we have to add the two displacements up. Okay, one for uniform motion, the other for uniformly decelerated motion. For the uniform part of the motion, the distance covered, of course, is just the speed times time. Speed is V0, time is delta T, so that is just V0 delta T. Okay, V0 delta T. And then you have to add to that how far he traveled during the deceleration stage between here and there. And we know how to do that, but the formula is V initial T plus 1/2 AT squared, right? V initial is just V0, right? This and that, they're just V0. So it's V0 times the time duration for the deceleration, which is between delta T and T1. So the time duration is T1 minus delta T. Right, that's the first one, V0, V initial T. The next term is 1/2 AT squared. 1/2 A is A2. Right? T is again the time for deceleration, which is T1 minus delta T, n squared. All right. Now you can see you can cross out a couple of terms here. This term cancels with that term. They're both V naught delta T, except there's a negative sign in the second term. So it's just V naught T1 plus the quadratic term was squared. Right. So you plug the numbers. V naught 25 meters per second. T1 is 1.86 seconds, and A2 equal negative 8.2 meters per second. Plug in all these numbers, you find delta XB equals what? Equals 39 meters. So before they reach the same speed, car A has moved forward by 36 meters. Car B has moved forward by 39 meters. So therefore the distance between them has shrunk by what? 3 meters, okay? Because car B has gained on car A by 3 meters. So delta XB minus delta XA equals 39 minus 36, and that is 3 meters, 3.0 meters. Okay, but remember, they start out with what? With 4 meters of separation. 4 meters of separation. You can see here 4 meters of separation, and so the distance between them has shrunk, but it only shrunk by 3 meters, which means they still have 1 meter left. So at the moment they have the same speed, car B is still behind car A by 1 meter. After that, of course, car B will be slower than car A, so therefore the gap between them will shrink, will start to increase from 1 meter. So therefore, there will not be a collision. Right? So this is the answer. This is less than 4 meters. So no collision will occur. No collision. Okay, so that is how we answer this question. In fact, if you follow the steps, the reason why we follow these steps is because we found this strategy of finding the solution to the problem. We need to look for the moment they have the same speed, because after that, if no collision has already taken place yet, it will never take place. So you have to figure out whether collision has taken place by that time, T1 or not. So you find T1 first, and then you figure out whether they have already collided by that time. And the way we do that is look at how far they have traveled each by that moment. Okay, so that's the order A, B, C, and D. That's how we solve this problem. Okay, so this is a two-body problem. The motions involved for not just one object but two objects, both in uniformly accelerated motion. We apply the formulas, well-known formulas for V and for T for uniformly accelerated motion. But to solve this problem, you have to think of a strategy. You have to play a little movie in your head and look at the sequence, how the event unfolds, and you can then figure out your strategy. Okay, so this is the first sample problem. Now let's look at the second sample problem. Okay, the second sample problem, you have a diagram like this. Okay, a person stands on the rooftop right here. Look at the person stands on the rooftop right here. It drops a stone at 0 speed from the rooftop. Okay. Drops a stone at 0 speed. A moment later, another person in the building observes the stone passing by his window in a time interval of delta T. So there's a person here, and this person watches the stone passing by his window between this point and this point. Okay, the height of the window is 1.7 meters. And how long did it take for the stone to pass by the window? The time interval is 0.230 seconds, delta T. Okay, so the first person drops a stone, okay, and that stone passes by the window of another person with a time interval of 0.23 seconds. And then the stone continues to go downwards until it reaches the bottom here. Okay, and looking for several things. Right? What is the average speed of the stone as it passes by the window? Well, how do you find the average speed? Distance over time. Do we know the distance? Yeah, it's just the height of the window, which is what? H. which is 1.70 meters. The time interval for that is also given as 0.23 seconds. And therefore, it's a piece of cake to find A. Okay, A is it's not much. V average equals what? Equals delta x, delta t. I've chosen x direction to be downwards for convenience. I mean, you can choose upwards, but since everything's going downwards, why not? Okay, so delta x in this case is just h. It's h, and just divided by delta t. We know what h is. It's 1.70 meters. Delta t is 0.23 seconds. And then you plug the numbers, you'll find the answer to be, the answer is 7.39 meters per second. 7.39 meters per second. That's a piece of cake, okay? And then look at part B. Look at part B. At what speed V is the still moving when it reaches the top of the window? So on this diagram, you mark this speed V here in yellow. I want to know what that speed is when it reaches this point. Okay, passes through, passes by the top of the window. So you're given the average speed. Okay, you're given the average speed, and you want to know the initial speed here. Here's the initial speed. Let me use a different color here. So here's the initial speed, which you want to know, and you know the average speed, which is 7.39 meters. You also know the distance traveled between here and there, and that is h. Okay, can you find the initial speed? Well, at this point, there are a couple of things you can do. Okay, there are a couple of things. Look at what you know. You know the distance traveled, you know the average speed, and you know the acceleration. Okay, so how do you find the initial speed? One thing you can do is to realize that the distance traveled, h, follows the displacement for uniformly accelerated motion, which is v initial t plus 1/2 at squared, right? V initial, this is the initial point. So v initial is what you're looking for, right? That's the v they're talking about, okay? V initial t plus 1/2 at squared. The distance traveled is h, right? And the time t is between here and there is delta t. So I can write for the movement sequence passing over the window, passing by the window, I can write h equals to v initial t. We call this v. We didn't call it v initial, just call it v. T, the time interval to pass the window is delta t. And then plus 1/2 at squared. A is just g. G delta t squared. Okay, you know what h is, 1.7 meters. You know delta t, which is 0.23 seconds. You know what g is. You're looking for what? V. You're looking for this v here. Okay, this v right here. So that's one strategy. So you have to know what they give you, and utilize the information they give you, and that's what you come up with. Okay. Another way to look at it, say, I know the average speed. The average speed is, as you know, v initial plus v final over 2, right? V initial is what I'm looking for. So the average speed. I'm going to start using the average speed now. So the average speed is v initial, v average equals to 1/2 of v initial plus v final. V initial is that v that I'm looking at, plus v final. But v final is related to v initial. Look, you start from here and you end up there. V final is greater than v initial. Why? Because there is an acceleration. Do you know how long the acceleration is taking place between here and there? Yes, it's delta t. So v final at this point is just v initial plus what? Plus at. A is g, t is, in my notation, delta t. So v final is v initial plus g delta t, isn't it? Right? That's v final. Right? This whole thing is v final. Okay. Let me label this. This is v final. Right? So that tells me what to do. I know what v average is already. I already got that from the first part, and I know what delta t is. I know what g is. I can solve for v. Now these two equations look different at this moment. They look different, but I can show you easily they're really the same thing. Okay, because after all, I know that V average equals D over is H over delta T, isn't it? So H over delta T equals, you know, whatever you find on the right hand side. All you have to do is move delta T to the right hand side, so you can solve for H, and that H should look just the same as this. Look, let's do that. Okay, if we move this delta T to there to the other side, then I get H. H is what? Is 1/2 delta T times this whole thing. What's inside? 2V plus G delta T. Okay, so 1/2 delta T times 2V. So 1/2 times 2, isn't that just V delta T, the first term? Just like what you see here, just like what you see here. Okay, and what do we have left? We have 1/2 G delta T times another delta T moved from the other side, isn't that 1/2 G delta T squared? Right? So these two expressions, even though you know, we look at things from different angles. The first we look at displacement, the second we look at the average speed, you yield the same answer. It doesn't matter. Everything, they're all related. Okay, so regardless of which one you use, end up with the same result. And all you have to do is then solve for V average. Okay, just solve for V average. I'm sorry, solve for V. You already know what V average is. You just solve for V, and you'll find this V when it reaches the top of the window. I can just write down the result for you now. V is equal to 6.26 meters per second. That's the speed when it reaches the top right here. The speed right here. Okay, of course, the average speed is greater because it's already been accelerated on its way passing the window. All right, so that's part B. Now look at part C. How far below the rooftop is the top of the window? So you're looking for distance H1 basically. Okay, you're looking for this distance H1 between here and there, H1. Right? How far below the rooftop is the top of the window, H1. So let's look what we know. We know the acceleration, and we know the speed by the time it reaches the top of the window. And looking for displacement from the rooftop to the top of the window. Since we know that, but we're not given the time, right? We're not given the time it takes to go from the top of the rooftop to the top of the window. So you don't want to use 1/2 GT squared because you don't know what T is. What we do know is the final speed. We do know the displacement, which is actually, no, we're looking for H1. We do know the final speed, which is given in part B, 6.26 meters per second. We do know the initial speed, which is 0. What formula relates initial speed at this point, final speed at this point, the displacement H1, and the acceleration G? Which formula relates all these things without any T in it? Which formula is that? Well, you recall that is the formula of V final squared minus V initial squared, or V naught squared, equals 2A delta X. So that's generic formula. A is G. Delta X is from here to there, and that is just H1. This is the best formula to use because we know everything except for H1. I can solve for H1 now. All right, so you know you have to figure out what they gave you and apply the correct formula using the most information they provide you, while avoiding too many unknowns, like in this case, the time it takes to reach the rooftop. They didn't give that to you. So H1 equals 2 V squared minus V naught squared, which is 0, divided by 2G. Okay, very easy math. And V is 6.26 meters per second. We just got it from part B. So you plug that in and you get H1, which is equal to 2 meters, 2.00 meters. So the roof, so the rooftop is 2 meters above the top of the window. Now, H1 is equal to 2 meters. And finally, how tall is the building? Looking for the entire height from the rooftop all the way to the ground. We already know what H1 is, which is 2 meters. We already know what H is, which is 1.7 meters. We're just looking for H3, right? We're just looking for H3, which add them all together. H3 is from the bottom of the window to the street level. Okay, so how do we find H3 then? Well, I mean, you can start from, hold hold on. We use a different color. Okay. You can start from here. You can start from this level, and you end up at that level. You call this initial and the street level final, and you can apply, h3 equals v initial t plus 1/2 gt squared. But the problem is, do we know the speed here at this point? Do we know the speed at this level? Well, I mean, we can find it out, but we're not given directly. We do know the speed at this point, okay? At this point, reaches the top of the window, and that's 6.26 meters. So why don't we apply this formula, the displacement formula between this point and the ground? We call this initial and this final, because we know the initial speed if we use this point, the top of the window, right? And then we can find the total travel distance between the top of the window and the ground. All we have to do is add h1, we can find our answer, right? So it's better to use that instead of using the bottom of the window as the initial, because we don't know the speed at that point. So let's apply the displacement formula between the top of the window to the ground. And I find the following. I find that h plus h3, that is a displacement, right? Between here and there, right? H plus h3. Isn't that equal to v initial t plus 1/2 t squared? V initial is the speed, the top of the window is just, we call it v, okay? And do we know the time? Yes, we do. When it passes through the window, the time interval is delta t, which is 0.23 seconds. And it also tells you that it took another 1.20 seconds to reach the bottom. So between the bottom of the window and the ground, it spent an additional time, 1.20 seconds. So v times what? Total time, which is delta t plus, we call it t3. T3, the time it takes to go from bottom of the window to the ground. So that's the first term, v delta t. The next term is 1/2 gt squared, 1/2 t squared. T again is the total time to travel from top of the window to the ground. And that again is delta t plus t3. Okay, square that. T3 equals 1.20 seconds right here. Okay, right here. And delta t is 0.23 seconds. G is 9.8 and V is 6.26 here. So you find H plus H3. Okay. And once you get that, then you can find a total height. All you have to do is to add another value, which is h1. So first of all, let's find h plus h3, and you plug in the numbers, you find the answer is 19.0 meters. And therefore, the height of the building H overall is h1 plus h plus h3. You know, add them all together. H1 is 2 meters between here and there. That's 2 meters, right? And then plus h plus h3. So the total answer is 21 meters. Okay, so that's how we solve this problem. So you see, between problem 1 and problem 2, you know, we're all dealing with uniformly accelerated motion, and there are a limited number of formulas here. You have the speed formula, you have the displacement formula, and you have the average speed formula, and you also have the v squared minus v initial squared business. That's the formula with now t in it. These are the only commonly used formulas we derived. There are 4 of them, and we utilize all of them. You can see between these 2 problems, and they all lead to the same thing. But some formulas are easier to use than others, depending on what you're looking for. The strategy is always, first of all, figure out what's going on. Okay, you know, you have to first play a little movie in your head, and you know, make sure you understand the sequence of what's going on. And secondly, look for, if you're looking for an unknown, first figure out what they gave you, the conditions, and look for a formula that utilizes the best, the most of what they give you, and while avoiding, you know, extra unknowns that they didn't tell you. This is the reason why when we solved for part D, we went from, again, we went from the top of the window, to the ground instead of from the bottom of the window to the ground. Again, the reason is we know the speed at the top of the window, which is already given in part B. So we don't want to use the bottom of the window as the beginning point, because then we have to go one extra step. We have to figure out the speed when it reaches the bottom of the window. And we can do this, but it's not necessary. All right, so hopefully give you some idea about the strategy of solving uniformly accelerated motion in one dimension. And then in the next lecture, we're gonna move away from that. We're gonna look at what happens if the acceleration is non-uniform. That is not the the key, the emphasis of the chapter. But sometimes we do have to deal with non-uniformly accelerated motion. And when the math is simple enough, we can actually solve it. So we see a couple of examples in the next lecture for that.